Okay, so on behalf of the CMU Portugal program, I'd like to thank you, all participants who have registered for the call. Also, a special thank you for Professor Eric Nyberg for his availability. This talk will be a part of a series of talks that we have named Data Science Talks at CMU Portugal, and that will take place during February and March, leading up to the advanced training program in data science and machine learning that will hopefully be launched this year. The session will have a duration of 1 hour, 45 minutes for the presentation and 15 minutes for questions in the end. So please keep your microphone muted and camera turned off for the session. Should you have a question, please use the chat to question Professor Eric, stating your name and affiliation. I will now give the floor to Professor João Magalhães from Universidade Nova de Lisboa to make a brief introduction of Professor Eric. Once again, thank you.
Thank you, João, and good afternoon to everyone. So it's my pleasure to welcome you all to the second talk under the initiative Data Science Talks at CMU Portugal. So as João just said, this is a series of webinars organized in the framework of this advanced training program in data science and machine learning. So today's talk is Eric. Eric is a professor at CMU in the Language Technologies Institute, where he directs the Master of Computational Data Science program at CMU. And Eric has made landmark contributions to the field of automatic text translation, information retrieval, and automatic question answering. So Eric is the recipient of the Alan Newell Award for Research Excellence for his contribution to the field of question answering and his work as an original developer of the Watson project. So this is very interesting because this is in fact the second time that Eric is giving a seminar in the context of CMU Portugal. The first time was almost 10 years ago in 2012. So I was lucky enough to be in that seminar as well. So at the time, Eric's talk was entitled Deeper QA, CMU, Watson, and the Open Advancement of Question Answering. So this was a very exciting talk at the time about this field. And I'm sure that today's talk will have a similar long-term impact. And today's talk is about autonomous driving. And Eric is once again pushing the frontiers in another fast-moving research area. So let's give the floor to Eric and see what Eric has to tell us today. Thank you very much.
Thank you very much, João and João, for the introductions. It has been 10 years, and I tell you right now, I would really enjoy another visit to Lisbon. It's been a long, cold, gray winter in Pittsburgh. So let's talk about autonomous driving. I'm going to do a few things with this talk. I'm going to give some introductory remarks about autonomous driving. I think we're all aware of what companies like Uber and Waymo have been trying to do. But I'll go a little bit deeper on what the technical requirements are for this. And then I'm going to talk a little bit about our data science program, which I've been discussing with Jamie and possible collaborations with the CMU Portugal program for your data science initiative. And then the main part of my work today is going to be focusing on the Roborace challenge, which is actually a capstone project being undertaken by the master's students in our Masters of Computational Data Science program. So not only is it interesting from a technical perspective, but from an educational perspective, this will give you an idea of the kinds of projects we're doing in our master's program. And certainly I would be happy to discuss with you prospects for doing similar kinds of projects in your data science program. One of the things that we believe is that you can't learn data science just from textbooks or classic data sets that everybody can download from the internet. You have to learn by doing and by engaging with tough, messy, large-scale, real-world data science problems. And this is certainly an example of a problem like that. So what is autonomous driving? So by definition, this refers to self-driving vehicles or transport systems that move without the intervention of a human driver. Since the advent of autonomous driving, the Society of Automotive Engineers has actually created standards for autonomous driving, and they define 5 levels of autonomy, from no automation to full vehicular autonomy. And as you can imagine, there are various policies and regulations associated with ensuring the safety of vehicles at each of these levels. And there's a link here that you can use if you want to follow up. There's a nice website that gives a lot of details about this. If we take a look at the Wikipedia definition of autonomous driving, we learn that self-driving cars combine a variety of sensors to perceive their surroundings, such as radar, LiDAR, sonar, GPS, odometry, and inertial measurement units. And by that, we can have, we're essentially talking about G-force detectors that can detect whether the car is moving to the side or not instead of moving down the track. So what we need in order to implement autonomous driving are very advanced control systems that can constantly monitor the sensor information and then decide how to control the vehicle. And that means deciding whether to push on the gas pedal, push on the brake pedal, turn the wheel, how much to turn the wheel, how quickly to turn the wheel. All of the things that we all learn when we learn how to drive by doing lots of practice on the road. Obviously, in a real world context, there will be obstacles. And when we are driving on sort of urban roads, there will be signage, signals, and so on that we're expected to follow. So our autonomous vehicle has to respect the red lights and speed limit signs, for example. So here's a picture from Uber Advanced Technology Group. We've had some graduates of our master's program that have gone on to work in this group and use the machine learning techniques that they learned at Carnegie Mellon to develop self-driving technology. So you can see that one of the Volvos that Uber has outfitted has 360-degree radar coverage for detecting objects around the car. It has a forward-facing camera array that can focus both close to the car and far away. So it can look for vehicles ahead that are braking, pedestrians who are maybe getting ready to cross the road in front of the car, traffic lights and various signs. There are top-mounted LiDAR units that can give you a 360-degree dimensional scan of the environment. So you have sort of a wireframe representation with depth that tells you everything that's around the car. And then you also have side and rear facing cameras so that you can combine those with the front camera to get a continuous view of the surroundings of the vehicle. And that's quite important as the vehicle turns around corners, for example. Now, of course, to integrate all of this, you need to have custom designed computing. You have to have hardware that can handle all of the sensor streams at the bandwidth where they are most effective. And some of these probably operate at very high frequency. So you have to have very good hardware that can capture the data in real time. And then you have to have sufficient processing units in the car to make sense of all of that data. And a lot of the machine learning work that we're going to talk about relies on being able to very quickly represent all of that information and then apply some algorithm to that information to decide what to do next, whether the autonomous driver should maintain the current course or change somehow the way that the vehicle is being driven. So I want to show you guys a brief 3-minute video that talks a little bit about the history of Carnegie Mellon and autonomous driving. In fact, Carnegie Mellon has been involved in autonomous driving for a long time, since 1985. When I arrived at Carnegie Mellon as a graduate student in 1986, I saw the blue van that you guys are about to see driving at 2 miles an hour, not on the roads, but on the footpaths of Carnegie Mellon every day when I rode my bicycle to campus. So for me, there's a certain amount of nostalgia in this particular video, but let me show you this one.
Since 1984, Robotics Institute have been working on the development of outdoor mobile robots. This research has produced results in the areas of perception, planning, and systems for autonomous road following in real-world conditions. Two testbed robots, the Terrigator and the NavLab, have been equipped with sonars, cameras, and a scanning laser rangefinder. The NavLab also carries researchers and computers on board, including a Warp supercomputer. By using the Warp, we can process an image every 2 seconds and drive the NavLab at 1 meter per second. Our color vision, 3D perception, recognition and mapping, and road following modules have achieved significant capabilities for navigating roads. These modules also provide a strong basis for our next major emphasis, cross-country navigation. It will require continual fundamental research and advanced development of vision, planning, modeling, and mechanism.
The strobe light is on. The command from the tower is to move. Ladies and gentlemen, Sandstorm. Ladies and gentlemen, your Kodak moment.
So you can see in this video how much the technology progressed over the years, from that blue van moving very slowly to vehicles that could move at much more rapid speeds across open terrain in the desert with lots of sand kicking up and vegetation and no clear road, to the vehicle in the urban challenge, which was able to navigate successfully in an urban environment while respecting all of the traffic lights and road signs and so forth. And some of you may already know this, but when the Uber Advanced Technology Group was founded, it was founded in Pittsburgh, just a few miles from Carnegie Mellon University. And many members of Carnegie Mellon's Robotics Institute who had worked on these autonomous vehicles were actually hired at Uber. And I can remember being interviewed by a journalist who asked me, wow, isn't this terrible for Carnegie Mellon University that all of your researchers left to go found this lab for a company? And I thought that was kind of not a great question, because to me, this was really a success because it showed that the technology had matured to the point where it was worthy of, you know, full-on commercial development, shall we say. Now, of course, we all know that there have been problems with autonomous driving in the real world and that there have been unfortunate accidents involving autonomous vehicles. And I think that we need, obviously, to do more research on making autonomous driving more robust. And that's one of the reasons why I personally got involved in autonomous racing. So you see the 4 systems we just took a look at in the video are placed on this timeline here. And then on the right side, you see 2020 Roborace. So that's the challenge that I got involved in through working with my master students in the MCDS program. So in the MCDS program, the students typically do 3 or 4 semesters worth of coursework. They have to take courses in cloud computing, human-centered data science, and machine learning. And they also have to complete a capstone project, which runs for 12 calendar months from January through December, split up into spring semester and fall semester. And then some of them work on their capstone in the summertime, but some of them also go off and work at companies in Silicon Valley or on the East Coast or whatever. So in spring of 2020, this group of students approached me and said, "Hey, professor, AWS has this challenge called AWS Racer. We think it's really cool, and we'd like to try this out. Can you sponsor us? And can we buy the Deep Racer hardware and play around with this challenge?" And I said, "Well, yeah, that sounds pretty cool. That's a good data science topic for you guys to work on." So we got involved in autonomous driving from the MCDS program in spring of 2020. And this wasn't at all from any big government grant or anything that was externally funded at all. It was just students working together within the program. But we were tremendously lucky that we had 2 mentors who were MCDS alumni who have been out in industry for several years now, quite successful. And in particular, Sita Ganju is a machine learning engineer at NVIDIA. And she's had a lot of work at NVIDIA related to reinforcement learning and autonomous driving. So the team really got off on a good foot. So their approach to this was not to think about engineering an algorithm where we would just write a big program that would constantly merge all the data from the autonomous vehicle and decide what to do. We wanted to use the latest techniques of reinforcement learning. And reinforcement learning is essentially a way of computing where you represent the physical environment of your robot or your vehicle. And then you have basically a way of interpreting that environment so that you can present a set of variable values to the robot. And then the robot has to learn some policy, which is how do I respond to this sort of representation of the environment. So for example, my representation of the environment might have a variable that says whether or not there is an object directly in front of the vehicle within 100 yards. And if that variable flips from 0 to 1, then I may have a policy that examines this variable and then says, oh, if this variable is ever 1, then you have to slow down until that variable becomes 0 again. You have to slow down and stop. Okay. So the agent is always going to react to the environment by looking at this constantly updated representation of the environment expressed as some set of variables. And then the way it learns is by being given a reward function. And then it just basically does a bunch of learning by doing until it learns how to maximize the reward function. So to give a silly example, the reward function obviously here would be maybe to go as fast as you can without hitting anything. But in the beginning, the robot doesn't know what to do. It's going to try every possible action. So it might see that this variable of something in front of the car is set to 1. And it may say, well, wow, that's the first time I've seen that. I don't know what to do. So let me try stepping on the gas. Okay. So then the vehicle is going to hit the virtual object in the training environment. and then its reward function is going to go to 0 because it failed the test. Okay. Next time it sees that variable, it's going to say, well, last time I stepped on the gas, I'm not going to step on the gas this time. Maybe I'll try stepping on the brake. Okay. And then that time it avoids hitting the obstacle, and then the reward stays high. So the way reinforcement learning works is that you're constantly updating the environment, and then the agent is applying its policy, and then it's trying to apply a policy that's going to basically maximize the reward function. So if we're racing cars around a Formula One racetrack, we want to be minimizing the amount of time it takes for us to get to the finish line, but we also want to minimize the number of obstacles that we hit. And we also need to keep the number of times that we crash the car to 0, or else we haven't had a successful driving. So I think the idea behind this is that rather than trying to code up an algorithm by hand, we'd like to use a virtual environment in the cloud and allow the reinforcement learner to drive many scenarios, millions of miles in the cloud, and then learn the right policy for driving, so that essentially it can deal with any conditions that it might encounter in a real world scenario. So during their first semester, the students investigated a lot of different autonomous racing virtual environments. I'm not going to explain these in detail, but I'm going to quickly mention them to you in case you're interested in following up. First was AWS Deep Racer, provided by Amazon. This is a nice environment because all of the infrastructure is provided by Amazon. And then you can basically get a grant to get these autonomous vehicles, and you can build a sort of a test track of your own for these things to run around in. MIT created an environment called Ducky Town, where essentially you could create different tracks like the ones that you see on the picture here, including a simulator and training environments, as well as the physical racing platform for these little ducks. And Ducky Town holds a competition called the AI Driving Olympics, which the students also basically tried out to learn about autonomous driving. NVIDIA basically put together 2 different race cars using the NVIDIA Jetson Nano compute environment. They're smaller, versions of real-world cars. They're easy to put together and build. And really, there were no racing competitions done with these. They were really put out into the public domain to stimulate work on the social impact of vehicular robotics. So, for example, being able to follow objects, or send these things out into the field to detect the formation of storms, for example, or some of the social impact applications that NVIDIA was looking into there. Also a learning to drive challenge, where basically the teams are given sensor data. So this is moving in the direction of Roborace, where the idea is to make it possible for lots of academic groups to work on autonomous driving, even if they don't have the physical hardware or the ability to send people out into the desert to gather, many hours of sensor data by driving the vehicle around. So this is a very important kind of milestone because it started to sort of create data sets that were large scale and heterogeneous. So we have lots of different camera angles from GoPro cameras. We have visual maps from different sources, and then semantic maps, meaning that we have GPS coordinates and locations of different objects that we can use to basically correlate with any camera data that we have to try and understand where we are. So at the end of spring 2020, the team had done a lot of investigating of these different environments, and they had done some preliminary work on AWS Deep Racer. But then they found out about Roborace. And one of the team members said to me, "Professor, this is just, this is an amazing challenge because Roborace is literally going to give us the access to real world Formula One race cars running on a real track. So we're not going to be playing with little duckies or baby cars anymore. We have to actually work with a real car that's, you know, a real weight with real physics on the track. And this is just sort of the most exciting thing we can imagine. And at this time, there were no North American teams participating in this Roborace challenge. So our team had to basically convince these guys that, you know, a team of unfunded students in a master's program at Carnegie Mellon, you know, should be allowed to participate in this challenge. So they basically got a winning bid together. And once that happened, then I had to basically spring into action, find some funding for them. And then I supported a team of students who worked on this full time during the summer of 2020, figuring out how we could get into the game. And even though we had a long-term vision about what we wanted to do with reinforcement learning, in the beginning, it actually took a lot of work just to understand how to control this vehicle based on the software stack that was provided by Roborace. So Roborace is a privately held company in the UK, affiliated with the Formula One race organization. The Roborace Challenge is the first global event for autonomous Formula One race cars. So, you know, we're going up to 200 kilometers an hour, I think, in these cars. And they're essentially full-size race cars that have had basically all the computation and sensors put into them. So the organization provides the vehicles and the software stack for running the vehicles. They also provide simulation software that you can use for training and testing your driving agents. So essentially what the team does is a lot of work in the cloud to try out different algorithms. And then when there's a competition, they wheel the cars out onto the physical track, they load your software in, and then, you know, when the green light goes, then your software starts driving the car around the track. And in the most recent competitions, you have to basically complete a certain number of laps around the track without crashing. And then you're the team with the fastest time for the multiple laps was considered the winner. So this sets up a very nice research environment because the research teams are responsible for working on the data science and the algorithms, but they don't have to invest in the hardware. So the reason I think this is a success story for education is that it is possible for a group of master's students to get involved in something that is so state-of-the-art without needing to have the university put a huge upfront investment into the hardware infrastructure. So I think this is somewhat similar to government contracts we've had in the past, where we might, you know, see DARPA, you know, putting out a bunch of resources, you know, for universities to use. But even in those cases that we saw in the video, CMU had to get real-world sponsors to pay for all the hardware in order to do that work. So I like this because it democratizes access to this kind of infrastructure. And as you guys develop your data science program in Portugal, you may want to think about similar kinds of engagements for your students where they can work on challenging, impactful data science problems without having to, you know, invest upfront in the physical infrastructure. So that's one of the, I think, meta lessons that I learned from this. So what are the goals? Well, the key goals of Roborace are to drive in the real world in real time on a real track, while the agent that's driving the car is receiving and responding to real-time updates, not only about the sensor data from the cameras and the GPS locator, but also information about virtual objects and waypoints. Well, what does that mean? Well, it means that while the car is driving around the track, it's going to receive information that there are obstacles in the track that really aren't there. They're virtual obstacles, but it's going to receive sensor data that makes it seem like there's an obstacle there. It's also going to receive information about waypoints or places where the car is supposed to drive. And the analogy here would be to a video game where you have to collect certain valuable items in a video game by operating your avatar in order to touch those items. So obviously the goal is to drive around the track as fast as possible without crashing, but now there's the added constraint of avoiding the virtual obstacles and also hitting the virtual waypoints or collectibles. So this virtual environment that's overlaid on top of the track is referred to as the metaverse by Roborace. And for me, this is really the most attractive part of all of this. The students in the team love the fact that it's very fast Formula One cars. The reason I like this is because it gives us an environment where we can start to experiment with an arbitrary number of obstacles and waypoints. And we can create environments that are more and more challenging with things popping up all over the place. And the algorithms that we work on that can learn how to respond in these environments ought to be able to do better by having that kind of training. So the idea is I don't have to set up real world situations with real world pedestrians or dummies, walking across the road. I can combine a real world environment with virtual objects that are being kind of overlaid on the environment. And the agent that's learning to drive in the car really doesn't have to distinguish between those. It can treat them both as realistic data that have to be accommodated. So we could drive millions of miles in the cloud with virtual pedestrians and virtual other vehicles and use this metaverse concept to overlay them on top of anything. So we could, for example, take a particular dangerous intersection in downtown Pittsburgh and then create an environment for that and then run autonomous drivers through that with all kinds of different conditions using different kinds of virtual objects. So for me, I think this is really going to push the science forward, and that's why I think this is an important challenge intellectually, as well as just fun, for driving race cars. So why is this hard? Well, it's hard because most current approaches use hardwired driving algorithms that are hand-coded by engineers. There can be some statistical learning involved here, but it's all learning that's based on a specific set of conditions that need to be optimized. And adapting to a new type of track or a new virtual environment always involves recoding, okay? So it's not really easy to take something that's using one of these implementations and then apply it to sort of general driving situations. And obviously we want to have an autonomous driver that can react to any situation that arises because we want it to be as safe as possible. Safer than human drivers, if we can even achieve that kind of thing. So our hypothesis is that automatic reinforcement learning will eventually replace these hand-coded algorithms for autonomous racing, especially when we use virtual environments to do the training. And I believe that the long-term impact is that self-driving cars could learn to drive by training in these synthesized virtual environments in the cloud on a wide variety of situations which occur rarely in real life. So that's the real problem, is that Uber ATG can go out and drive their cars around on the roads in Pittsburgh 24/7, 365 days a year, but they're still not going to encounter very unusual conditions that have to do with certain kinds of storms at certain kinds of times of day, with certain kinds of precipitation and the effect on the lighting and other vehicles. Those are the situations where we fail as drivers because we're not used to them and we don't anticipate what could happen. But there's no reason why we can't create those conditions in a virtual environment and then train our autonomous drivers to react to them. So to give you an idea of what Roborace's roadmap looks like, the challenge is going to proceed in stages. Right now, we're in stage 2, where there are static objects everywhere on the track, and these can pop up in front of your car. So after it's done a lap, when it's coming around for the second lap, some barriers might appear on the track. So you don't know where the barriers are going to be before you start the race. So you have to do real-time dynamic path planning based on the signals that you're receiving in the vehicle about what's down the track in front of you. In the next stage, they're going to introduce dynamic objects, which means there'll be other cars, other virtual cars on the track with you, but they're going to be pretty predictable. They'll be following a fairly predictable path. They're not going to be trying to get in front of you and then slam on the brakes in order to impede you the way it might happen if you were driving against another human in a very competitive race. Then I think in the fourth stage, it'll be the first time we get into a real competition, but you're not going to be racing another physical car, you'll be racing a ghost car. But otherwise, to the driving agent, it will seem exactly like there is a physical car there in terms of the sensor data. And then the final stage will be real wheel-to-wheel racing, where you'll have real physical cars, many of them racing on the same track at the same time. And as you can imagine, things are staged this way because the further you go in this hierarchy of challenges, more expensive the mistakes are, okay? And in season beta, which we just finished, there were some teams that crashed the cars into the wall, which is quite unfortunate. And the chance for very expensive damage goes way up when you have several vehicles racing on the track, you know, with autonomous control. This is another thing I really like about this challenge is that there is no end to how challenging this can become. They're not stopping at a certain level where the competitors can basically overfit their solutions to that level. Everybody knows that in the end, you're going to have to be driving against very adversarial agents in a very realistic environment. And this is one of the reasons why we're thinking about reinforcement learning and doing lots of training in the cloud as the right way to do this, rather than hand coding a particular solution for each level of the challenge. So in the events that we participated in last fall, that was our first event, so we did not participate in the first season alpha, but we did participate in season beta. We ran 2 events and got second and third place out of 6 teams that were competing. The event was streamed on Roborace's Twitch channel. So if you go to Twitch and look up Roborace, you can actually replay the live stream and sort of watch this. It was kind of cool to see what happened there. And you can also crash. Most of the media was all about the car team that crashed rather than the cars that made it around the track. Sort of talked about what we did and sort of how we were successful. But to be honest, we succeeded by going around the track as fast as possible without crashing. But we didn't really try very hard to avoid the obstacles. So I think we smashed into 19 out of the 20 obstacles. At MIT hit all the obstacles, and we hit one fewer than they did. So the outward view of this was that it was a huge success because we had never done it before. But within the team, there was a lot of honesty and soul searching about this, and we realized we really have to do something to deal with dynamic objects. So there's a lot of work yet to be done. So what does reinforcement learning do for you? So now I'm going to show you what happens when you take this policy training procedure and you let the car kind of learn what to do based on the sensor data. So this is going to be reinforcement learning without a trained policy. So this is the car that's just starting out from scratch, trying to learn how to drive. So you can see it's not very certain of what it's doing. It's kind of making very gross motions, and then it crashes very quickly. So it doesn't really have a good idea of what's going on. Now we can take a look at the same vehicle, but now it's running a policy that's been trained by many, many hours of simulated driving around the track. And we can see that it's driving a lot in deliberate motions. And So this one gives us a bit more confidence that it's really learning how to drive. It's still perhaps making adjustments that are a little bit more jerky than a human driver would, but it's driving train policy. Now, it's not maneuvering around obstacles yet, but it's actually making a lot of progress. And the interesting thing about this is that the difference between what you saw in the first video and the difference and what you saw in the second video cost us somewhere between $5 and $10 in the cloud. So really did not require a lot of computation in order to train that model to be better. So this is why Roborace likes us, because we're thinking ahead to incorporating reinforcement learning to sort of move the state of the art ahead. And what the team is working on now is an environment that will allow us to run many, many, many experiments around many tracks with many conditions, so that we can leverage this cloud-based training, to build better agents. So what you saw there required thousands of iterations in order to figure out the right policy for driving around this particular track. And you can see here that there are many paths that don't go all the way around the track in the simulator. But you can also see that the reward function is going up here. If you look at the graphs on the left, the amount of time that the car is spending on the track without crashing is also going up. And then the average speed of the car is going up as well. So the team is literally creating different learning algorithms and then running them to see whether or not they are getting better over time by using these three measures, essentially, to decide which algorithms have promise. And then they let the ones that are doing well continue to run in the cloud, and then they stop the ones that don't appear to have promise. So it's a great environment for sort of multi-strategy learning. And this is where I think things are going to start to get really exciting, because now we have the possibility of training multiple kinds of algorithms to sort of see, which one is really going to be the best. I've already talked about reinforcement learning, so I'm not going to go over the slide again, but there's a link here to OpenAI's website about reinforcement learning. And any of you who are interested in getting into this or having your students investigate, I would definitely take a look at the open source software that OpenAI provides for reinforcement learning. Really a great resource for students to learn about training reinforcement learning agents very quickly. So our environment interacts with the simulator that's provided by the contractor Arrival, which provides the simulator software for Roborace. And we've created a camera interface, sensor interfaces, and then a way of plugging in a reward function, and then the action interface to control all the various actions in the car. And then we're working on how to plug in these model-free deep reinforcement learning agents. So the idea is we want to get other schools involved. Basically, anybody that learns how this works and who understands reinforcement learning should be able to use our reinforcement learning environment, which I just showed you, to plug in new novel algorithms for doing the reinforcement learning to learn new policies, hopefully that are even better than the ones that we have. So we're starting to think about branching out to collaborating with other schools. I'm going to skip over those slides. So in the near term, we're actually going to be publishing the first generation of this reinforcement learning environment. And we're going to be targeting conferences. And there's some links to some relevant conferences here if you guys are interested. And we're probably going to hold a workshop and a tutorial on how to use this environment. And we're in discussion right now actively with Roborace to get a free academic use license for the executable of their simulator. Then we'll be able to give everything that we have to any other university that wants to get involved. And I'm excited about that because I think that that's also going to allow a lot of innovation without a lot of entry cost for other universities that want to get involved. So if any of you are, interested in getting involved with reinforcement learning for autonomous driving, please follow up. We'd be glad to chat with you. And if you're interested in, trying out this package and maybe getting involved in the research, maybe in the context of your new data science program, this could be an interesting thing for us to follow up on. So obviously, we still need to do more work on our agent. We're looking into some important work that's been done at OpenAI on what's called learning dexterity. There's a link there for you guys to follow up on. There's a focus on a couple of papers from Google DeepMind. And then we're bringing in the next year's capstone group now. And we're going to be getting them to focus on these newer results. And then we also want to start working this year on competitive self-play, where we start to change the environment to make it harder as the agent gets better. So once we have agents that can nail driving around the basic track, we want to start, incorporating virtual objects and making the situation tougher and tougher. So I've got some other links here to some other related work. I'm not going to go over them. I'm just including these here for any of you that want to follow up on the academic side. And just so to recap, we built our Generation 1 reinforcement learning environment that was used to produce those videos that I showed you guys. Now we are about to publish our first open version of this for the community, and then organize a tutorial where we start sharing this and then teaching this. But we're going to continue to compete in Roborace and hopefully use our own environment to do lots of virtual driving in the cloud, so that we can switch out the hardwired algorithms and actually compete with a reinforcement learning algorithm in the real world Roborace challenge in 2021. Okay, thanks for your time. Thanks for your attention. I'm ready to take any questions that you might have.
Thank you. Thank you very much, Professor. So we do have here some questions already. The first from Breno Melo. Besides NSL, KDD, and KDD99, is there a data set with real data from the vehicular network?
Yes, I think that if you follow the links that I have there, you can find them. But also, if you send me an email with a request, I'll have Jimmy Herman, who's the manager of all of this, send you links to all of the stuff that's available, because I'm sure he has a list of all of the links that are available. And next time I give this talk, I'll have that at the end of the talk.
Okay, thank you. Other question. One of the biggest issues in Formula One is the larger number of accidents which happen on track due to excessive speeds, and not only. Do you believe the learnings from Roborace can lower the number?
We talked a lot about this, especially when we think about adversarial driving, and any kind of Formula One or NASCAR racing involves human judgment, which is risk-taking, right? So when you cut off another driver or squeeze them out against the wall, you're making a bet that they're going to back off, okay? And sometimes they do and sometimes they don't. And there are still many accidents that happen. So I think that what we've talked about is you want to be able to control the risk-taking behavior in the computer, and go from something that slows down to 1 mile an hour whenever it sees an object pop up on the track, and then goes very, very slowly until it can really understand whether that object is going to be a well-behaved object or a chaotic object, because it might cause a crash. But then we also want to explore what happens if you have the most risk-taking behavior, where essentially you change nothing about your own trajectory until essentially you know that there is going to be an accident within some time window of predicted future motion. I think, though, that by utilizing this virtual driving in the cloud technique, you can definitely simulate many different kinds of situations, so that, for example, in an urban environment like an autonomous taxi, would be much better able to drive defensively and recognize when other vehicles are behaving erratically. But I think that when you get into the real world stuff in Roborace, we really do have a mandate to not crash the cars. And I think that one of the big challenges for reinforcement learning is, what if the Society of Automotive Engineers came to you and said, okay, in order to classify for a level 5 autonomous vehicle, you have to show me sort of how I know what your algorithm is doing. And you have to prove to me, that your algorithm will never crash under, these, constraints on the set of conditions that you have. And that's tremendously hard for, machine learning algorithms to do because they're typically not very transparent. I do think, though, that to answer your original question about reducing crashes, I think that being able to study behaviors of other cars and then predict whether they will cause accidents or not could lead to the idea of having onboard systems for human drivers, which are basically watching other drivers and then giving some advice about what those drivers may be doing, or predicting what their motions are going to be. And that's one of the things our team is starting to look at now, is sort of using machine vision and the forward-looking camera to watch other vehicles and to try and predict, I think, what they're going to do.
Yeah. Other question from Henrique Cardoso. Are you using mechanisms to ensure safe RL? That is, can RL continue in the real world or just in simulation? And if so, what are the challenges to ensure robustness and safety constraints?
Great question. So one of the things that we are quite aware of is that we can train the RL model. Let's say it's a beautifully sunny day. Sun is, at 12 o'clock, no shadows on the track, no rain, and very well-behaved vehicles that are on the road with us. And we know very well that we could probably give a very high certainty, 99.99%, that in those conditions, a crash will not occur. And the way that we would do that would be to basically say that we have simulated millions of miles of driving under these conditions. And, we haven't had an accident in the last, 999,000 miles of driving. Okay. The problem comes when you have to predict what can go wrong. And that's where we get into recognizing that there's another vehicle with erratic behavior that you haven't seen before. And that's when you automatically have to have an agent that becomes much, much more conservative. Maybe even it just pulls over to the side of the road and stops driving and says, wow, I am sensing something that I have never seen before. Maybe my sensor is broken, or maybe there's really an erratic driver out there, but I'm not going to continue to drive down this road because I can't predict what this guy's going to do, and I have to maximize safety. Or, wow, the weather conditions are getting so bad that I've never been in conditions like this before. I'm going to pull over to the side of the road and wait. Okay. And that's more human-like behavior. Maybe some of you guys have been in terrible fog or a terrible hailstorm or terrible rainstorm where you really couldn't see well enough to drive. And we all know that you have to pull over to the side of the road in those situations. So I think what's going to happen is that we're going to get approval to use reinforcement learning in the real world, but with some guarantees about what are acceptable operational environments. And I think what's going to happen is that, SAE is probably going to come up with standards where, certain reinforcement learning algorithms are only allowed to operate under certain environmental conditions, let's say. And part of the safety checks are going to revolve around the idea that when those environmental sort of constraints are violated, the vehicle has to, pull over to the side of the road and shut down.
Okay. Another question from Don Arpster. As your team consulted with actual race drivers, there are other factors besides just object avoidance involved in racing, such as pavement temperature impacts, how sticky tires are, and also how fast your car can go without flying off the track.
Yes, and in fact, this is why you have accelerometers in the vehicle, temperature sensors, because of the fact that the tires do warm up on a hot day. And this is why you have to do the reinforcement learning under all kinds of different conditions, because when the tires are hot and sticky, the car is going to respond differently to a certain movement of the wheel than when the tires are cold and when it's rainy outside. So the team is aware of all of those variations in the conditions, and they are trying to map all of the sensors into that variable representation of the driving environment, so that they can both vary that in simulated environments, but also learn how to react. So being able to incorporate the strategies of real world drivers is really important. And the question is whether or not the sensor data is going to be sort of as useful as, sort of a human being in there kind of having the feeling, through the seat and through the wheel. There's an assumption that that is the case, but I'm sure that, pro drivers perhaps have a very finely tuned way of sensing this that may be harder for a machine, to sense, from the sensors that are available.
Okay, so we have received now three more questions, and then I will ask them, and then we need to close. But the first one from Professor Miguel Boto: different cultures have different driver reactions while driving. This will mean that a general car maker have to use different RL strategies depending on the country or continent the car will be traveling. Is this a serious constraint to the autonomous driving software development?
That's really cool, because I hadn't thought about that. But I have to tell you, after my first cab ride in Rome, I really learned this 100%. So, guy driving like mad, and then also stopping very quickly to allow a beautiful woman, to cross the street. All of a sudden, he became a very nice guy, really crazy stuff. Absolutely, you would have to do this. And I think that's a really nice way of thinking about what we call domain adaptation, which is basically you have to take very seriously the idea that the environment is not just the weather and the time of day or the time of year, but also what kinds of roads, how the roads are intersecting, what buildings are around, whether there are a lot of pedestrians. And then, as you say, how are all of the other drivers reacting? So my guess is that what we would have to do is find a way to simulate those kind of behaviors in the virtual cloud learning environment. And then we would have to create, agents that are able to draw upon that driving experience, so that, if I'm driving in Omaha, Nebraska, I have a different model than if I'm driving in, downtown Rome, for example. So yes, and I think that's actually going to be part of the serious testing of reinforcement learning is going to be to talk about, can you do something that works in all environments, or do you literally have to narrow down the training for a specific environment in order to get good enough at that environment? And maybe you would have to, if I think about that. If you become very good in one environment, you may not be as good in another environment. So you might have to have, variations on the learning agent depending on where you're driving.
Okay, so a question from Ruben Araújo: do you believe autonomous driving will become a reality in the next 10 to 15 years, or will it be a kind of fusion technology and biosensors that would require some input from the human driver?
So my personal answer to this is that I think that fully autonomous vehicles will get approved, but in very limited contexts. So there are already robot drivers that are driving huge mining trucks back and forth in an off-road environment, way down into the mine, getting filled up back out of the mine, to be unloaded, because it's such a simple environment with no pedestrians and no weather and no safety concerns, that the current level of autonomy is just fine. We may never find something that can autonomously drive a cab around in downtown Rome without having some, human input. And I like the idea, actually, of having more of a fusion between man and machine, one of my PhD students is actually working on basically human-robot dialogues, where the robot is attempting to achieve a task and then the human is speaking to it in natural language, maybe with a headset. And I believe that actually is going to be very important, not only for real-time driving, but also for training. So I want to make my students' life really complicated. When they're training their thing in the cloud, I want to be able to watch what's going on there, and I want to be able to give hints by saying things like, oh, you should really try to slow down before you bank into turn 3. Okay. And maybe if I say that and then the reinforcement learner can understand that, then maybe I can shave off $100 of the cost that it's going to take for it to converge on a good algorithm, for how to drive around the track. So I really like the idea of having human coaching during training and also having final systems that do incorporate human input. And I believe that there will be tasks where the best performance will come from a combination of human perception and action and machine perception and action. So if we think about things like docking the space shuttle in space, clearly that's an environment where you can have much of the work being done automatically, but there may be very fine-grained controls and adjustments that have to happen in real time in very critical situations where a human has to take over. Yeah. So I believe that for critical applications, we probably will never become fully autonomous because the risk and the cost of a potential failure will be too high. Unless, the humans are, not better than the machines at a particular task, which is also, quite possible too.
Okay, so just a last question from our participant, Luis Conde. Energy efficiency policies in electrical vehicle race competition is proving to be a game changer. Do you think that in Roborace, this competing goals, fast but efficient, can gain from RL approach? And do you foresee that it can be useful in real-world traffic management?
That's an awesome idea. I haven't been thinking about green initiatives at all in the context of Roborace. But yes, if you had a way of, you would add to the reward function of the reinforcement learner, sort of minimizing the amount of fuel that was being used. And then it would learn where perhaps there was no benefit in accelerating more quickly. It would learn that it could accelerate more smoothly up to a top speed. And maybe it would lose, a few seconds off the final time, but it would conserve a lot of gasoline. So yes, I think reinforcement learning could learn this. And I think that it would not be difficult to consider adding fuel efficiency into the reward function for training autonomous vehicles in real world scenarios. In fact, that's what you'd want to have because that typically also promotes smoother driving and smoother, more predictable driving in the vehicle as well in the real world. So that's a great idea.
Okay, thank you. I don't know if Professor João Magalhães has a final question.
We already had plenty of questions, yeah. So I really just wanted to thank you, Eric, once again, and thank also everyone for attending Eric's talk. So we're going to have another seminar in 2 weeks, and so pay close attention to your emails. The announcement will follow. So thank you very much to everyone, and especially to Eric. So,
thanks for your time, everyone. It was great talking to you today. Take care.
Thank you too.
Thank you, Eric.
Take care. Bye-bye.